presentation, we actually have two presenters from Uber. The one is Shouheng, and the other one is Steffon. I think both should be there already. So let me check if, 1 second. There you go. Okay. Yeah, I think both should be audible and visible now. I can see Steffon already.
Robin.
So, yeah. And I think now you should be also able to share your screen.
Okay. Can you see my screen?
Yes, perfect. Yeah.
Fantastic. So let's jump in. Hey everyone, my name is Steffon Davis. I'm the product lead for the data mining and analytics group at Uber Advanced Technologies.
Hi, I'm Shouheng Yi. I'm the tech lead.
And today we're going to be looking inside Uber ATG's data mining operation. Specifically, we're going to be looking at identifying real-world scenarios at scale for machine learning and motion planning. So we're going to go through 7 sections and then a Q&A. First, we're going to do an introduction to the topic. Second, we're going to look at how data mining is used for performance improvement flywheels. Third, we're going to look at some example data mining analyses. Fourth, we'll look at some example data mining outputs. Fifth, we'll look at how data mining is used in machine learning workflows, and then how it's used in motion planning workflows. And then we'll look at the data mining and analytics technology stack. Okay, introduction. So why self-driving at Uber? So self-driving matters for the world. It saves lives, saves time, and saves space. And self-driving matters for Uber. Providing safe, reliable, cost-effective transportation is Uber's priority. And Uber matters to self-driving. Uber's network allows Uber to scale self-driving globally. Okay, let's jump in. Data mining powers performance improvement flywheels. So we're going to be looking at 5 different flywheels that data mining powers. The first is perception and prediction. So data mining provides machine learned models with comprehensive, diverse, and continuously curated training examples. This has the effect of increasing model performance metrics such as precision and recall, decreasing training time, and decreasing overall compute. Second, we're going to be looking at how data mining provides for motion planning capability development with scenario-based requirements. This has the effect of increasing test pass rate and lowering interventions rate. Third, we're going to be looking at how data mining provides for labeling, targeted labeling jobs with comprehensive, diverse, and continually updated examples. This has the effect of increasing label quality, increasing label production speed, and decreasing production cost. Next, we're going to be looking at how data mining provides for virtual simulation, data-driven specifications for tests aligned with real-world scenarios. This has the effect of increasing test quality, increasing the efficiency of each test run, and lowering the overall compute cost. Then finally, we're going to be looking at how data mining provides for safety and systems engineering, statistically significant specifications and capability requirements aligned with the real world. This has the effect of increasing overall development quality, increasing overall development speed, and decreasing overall development cost. Okay, to orient ourselves, let's look at an example data mining analysis for something very specific. Let's take a look at pedestrians crossing the street. So to start off with, we'll look at the sample of data that's used in this analysis. So to collect this sample of data, a self-driving vehicle drove around this neighborhood. It's hundreds of miles of driving over dozens of non-consecutive hours. And you can see that as a result of the crisscross driving pattern, each intersection has more miles than the straights. The height of the lines indicate the volume of the miles. That's a result of driving vertically and horizontally through intersections, essentially looking at them twice. This is a heat map showing the time of day that those miles were collected. As you can see, most of the miles are collected in the morning and in the afternoon. And it's important to keep in mind these, the nature of any sample in a data mining exercise, because an ideal data set would cover every single road equally at every time of the day equally under every single weather condition equally. But without that, it creates selection bias. So the results we're looking at really have not much to say around what may have happened at night or on the weekends. So in this sample, as the SDV is driving around the neighborhood, the perception system is recording observations of all of the pedestrians that it sees. These are pedestrians on sidewalks, pedestrians standing still. But what we're interested in is specifically the detections of pedestrians where they're crossing the street. So to find those, we have to data mine every single pedestrian detection to find the scenario of when they are crossing the street. So visualized here are individual detections playing back, selected for the ones that are crossing the street. So after performing this data mining operation for this sample of data, we find 2,404 mined crossings from start to end. So this visualization is showing the start point and the end point, and then the overall path that the pedestrian took when crossing the street. Okay, let's explore these 2,404 mined observations. So to start with, let's take one dimension, specifically the average crossing speed. So in this plot, we have the 2,400 observations plotted with the average crossing speed. The fastest crossing is called out, and you can see the visualization of that crossing. And the slowest crossing has also been called out. And then the box plot is showing some summary statistics, including that the average value is 1.39 meters per second plus or minus 0.019 meters per second with 99% confidence. This is the same 2,400 observations, also plotting average pedestrian velocity, but this time as a distribution. We've also added a classification to this data to reveal moderate and extreme values. So the blue moderate values is essentially reinforcing that clump of values that we saw in the previous plot, and it's showing the average crossing speed at kind of the height of that bell curve. But this distribution also reveals that there's a second bell curve, that this is in fact a bimodal distribution, and the red extreme values actually reveal joggers that are crossing the street. And these joggers have an average jogging pace of about 2.7 meters per second, which is about a 10-minute mile pace. Let's add a second dimension to this. So this plot is, again, showing the average pedestrian velocity, but now we've added the distance traveled on the y-axis. In addition, there's a second classification that's been added to this data looking at the frequency of the crossings. So the blue values are crossings with values that are both common and moderate. The yellow values are rare crossings with moderate magnitude. And then the pink dots are the rare and extreme values. So one of the insights we can grab from this new plot is, especially looking at that clump of blue values, is again, the average velocity is about 1.39, 1.4 meters per second, but the common and moderate crossing distance is about 18 meters. Let's add a third dimension onto this. This time we've added road width, and this visualization is really capturing the intuition that variations exist within a scenario space. So we've got the same three classifications again, this time with that third dimension, which is establishing, well, it's revealing an intuition that yes, the greater the road width, it's also in general, the greater the time that it takes to cross that wider road. This is zooming in on that common and moderate blue bulk, really just to kind of emphasize that there are topologies of variations within a scenario space, and those common and moderate values do cluster together, yet that the set of rare and extreme values in that very wide pink space is a larger segment of the pedestrian crossing the road scenario. Now, we looked at 3 dimensions, but you can add an arbitrary number of dimensions. You can analyze a scenario in n dimensions. So this is showing 4 additional dimensions of the pedestrian crossing the street. And again, the concept of a scenario space remains, except now you can see it across n dimensions simultaneously, and you can see how like the gray areas reveal just a kind of more nuanced geometry of the scenario space. And to make a kind of cross-industry connection, this is a visualization that the Waymo simulation group published. Same concept. It's taking a scenario with multiple, an n number of dimensions. You can see here that this visualization that they produced is highly geometric, produced by artificially sampling different values. And that's in contrast to this visualization we were just looking at that's using real data points. Now, the last segment for our case study here, a very common question is, how many observations are enough? So in this first chart, it's taking the same 2,404 pedestrian crossing the street observations, and now it's plotted with the average crossing speed in the order that they were collected. And in this second chart, it's showing the cumulative average with the 95% confidence interval. And you can see that as you collect more observations, the confidence interval tightens up around that estimate of the mean. And in the third chart here, it's plotting the margin of error that really highlights that that confidence interval is tightening up and the margin of error is decreasing as you get more observations. So now let's say that you have a use case where a margin of error of 0.02 in your measurement is satisfactory. That's a satisfactory margin of error. Well, you can see that that's at about, you achieved a margin of error of about 0.02 at about 1,000 observations, which yielded an estimate of the mean at about 1.39. And that each additional observation after that really confirms the value that you arrived at after 1,000 observations. So in a sense, all of these observations after the 1,000th weren't strictly necessary to arrive at a confident estimate of the mean. Okay, so we looked at a specific analysis, but the process of data mining can produce a wide variety of outputs beyond the specifics we just looked at. For example, data mining in the terms of SDVs works a lot with raw data. So this is even before a model has been produced. So you can data mine where and how much an SDV drove, when an SDV drove, under what weather conditions, what was the luminosity that was present in the camera? Was there a lot of glare? Was it a very clear day? Was it at night? And what were the vehicle dynamics? So how fast was the car driving? Were there any hard brakes? Now, from the model detections themselves, so what the perception system is seeing, for example, you can then mine the actors. So you can mine the pedestrians, you can mine the vehicles and their attributes, you can mine the map itself. So the nature of the road widths and the number of intersections that you saw, and you can mine model performance metrics. So like, what were the precision and recall scores? What was the intersection over union score? From this, you can then mine higher order concepts. So from the actors and their interactions with the map, you can reveal scenarios, or from the maneuvers the SDV was performing, you can reveal capabilities and when they are exercised. And then finally, you can apply statistics to any of the below outputs. So for example, you can characterize those scenarios, or you can create confidence intervals around the characterization of actors, or you can balance log sets based off of capabilities that were performed and the time of day and the weather conditions. Okay, great. So we've looked at these types of data mine outputs. Now let's look at how those outputs and data mining powers a autonomy development workflow, starting with machine learning. So a high-level data mining powered machine learning development workflow starts with collecting data that's then mined. Those mined outputs are used to create prioritized labeling queues, and those labeled outputs are then mined again. Those outputs are used to balance the train, test, and validation log sets for model training, and those model trained outputs are then mined again, which then completes the loop. And this loop can continue over and over again with previously collected data and then with new data as it comes in. So let's look at each one of those steps individually. So starting with raw data when it's collected, and this can be before a model has even been trained, you can start with mining where and how much the SDV drove, when the car drove, under what meteorological conditions it drove, for example. And then those values can be balanced to create a prioritized labeling queue. Like, for example, you don't want to label the same piece of road over and over again, or the same time of day over and over again. You really do want to balance that labeling queue to get good representation. So let's say you have those labels now. Well, you can mine those labels, for example, the actors that have been labeled and the map that has been labeled, to reveal higher order concepts like the scenarios that were present. And then you can apply statistics to those to characterize those scenarios that were present to then balance the log sets for training. So now you've trained your model and it has created model performance metrics such as precision recall or intersection over union. And with those values now present with the data mine values, you can contextualize them across all of these data mine outputs. So where did my model, under what scenarios did my model perform best? Under what capabilities did my model perform worst? Under what types of road did my model perform best? Under what weather conditions did my model perform worst? So with that insight, you can see where the model needs to be improved. And the data mining can then take place again over all collected data. So whereas a portion of the collected data has been labeled, indicated by the black squares here, in general, there's a lot of other data that you can now apply the trained model to get detections, to then mine those detections to find more examples of the area where the model is weak. So for example, if the model is performing poorly with pedestrians crossing the street at night, then you can use the version of the model that has been trained to run it over collected data that is at night to find more of those examples to then prioritize them for labeling. And then finally, with the model performed on the car and the car collecting more data, all of that data now comes with detections from that model, which can then be mined as they come off the car, restarting this workflow from the very beginning, from when fresh data comes off the car. So to make another industry connection with this segment of the workflow in particular, Tesla talks about their data engine, which is a very similar concept to this, right? You have a data source like an autonomous vehicle. It's recording when the models are struggling or inaccurate. You can then flag other cars with those same, detecting those same moments where the models are struggling to collect more of those examples to then label, to then train over again to improve that specific capability. Great. Let's look at a second workflow. So how data mining impacts the motion planning development process. So a lot of it's similar, and I won't go over the areas that are similar, but motion planning has a kind of sidecar development process to model training. And it will take the data mined outputs shown here and then use it to develop requirements. So, given that this is how pedestrians cross the street, what are the safety, policy, et cetera, requirements that need to be in place to handle that scenario? And then those requirements and those characterizations from the real world are used to create simulation tests to then test that motion planning capability. Now, interestingly, with the scenario mined from the real world, those results from the virtual simulation test that were designed from the real world, those pass-fail results can be projected back onto the operational domain. So this is a visualization showing where the scenario was detected and then on real streets, and then based off of the rapid iteration loop, development iteration loop that's coming off of simulation, those pass-fail results are then projected back onto the road to get a sense of how the SDV would perform on those streets without having to drive the SDV on those streets over and over again. Great, and now I'm gonna pass it off to Shouheng to talk about the data mining tech stack.
Thank you, Steffon. Next section, we'll dive into the tech stack. We'll examine closer on how it's built. Next slide. Conceptually, there are 3 distinct steps to drive higher level concept at ATG. Going from bottom to top, we need a storage layer, we need a mining layer, and we need an analytics layer. Next slide. So we'll go through the big data warehouse, which is our storage layer. Next one. Imagine we have variety of data producers at ATG. The data producer could be about a SDV log, a self-driving vehicles log. It could be a map. It could be the ML performance. So I imagine that we have a pseudo data producer here on the right, where we yield a generator of structured data. Next one. Next, we want to ETL those data to a data lake. It could be any data, any file system that you choose. And at this point, the data landed in the storage as files. It could be in any format. It could be JSON, Parquet, etc. However, just want to point out, at this point, data is not very accessible to developer or data scientist. It's not really queryable. Therefore, another necessary step is needed. Next slide. We need to apply a data model to those unmodeled data files and promote those to queryable tables, i.e. we utilize a lot of data warehouse. It could be Hive, it could be Presto, and then we can translate those unmodeled data file into nicely queryable tables. Next one. Well, once we have those tables at our fingertips, we're able to utilize a lot of the analytics and visualization tools that we have at ATG. Let's say the most common one is the Jupyter Notebook. You can do statistical analysis on top of those data. You can throw the data on a map. We have a map visualization tool. And you can drive statistical inferences or machine learning model on top of those data. Next one. Having those data available is not enough, because we need to find the needle from the haystack, which means that we need to mine those data effectively. Next slide. Imagine our data producers. Most of the time, they're producing time series. So imagine you have LiDAR points, right? And you have images. Each of the sweep have a timestamp associated to it, which means that for most of the time, we need to be able to work with time series data. Figure on the right illustrate what we've been dealing with most of the time. So you can imagine each object here, the yellow dot could be a pedestrian, we'll observe the pedestrian from a start time to end time. Naturally, those are time series. Next one. So we can apply a specific heuristics or rules, we call it, to those objects. For example, we can write a heuristics, either it's a rule-based or ML model-based, to identify pedestrian crossing the street. Let's just say we identify object 3 as a pedestrian crossing the street. Next one. Then we can, as soon as we clearly define the rules, we can scale this up on the existing data set, and we can identify all instances where we see pedestrians crossing the street. And that's where you go from raw time series data to mine data, and the figure on the bottom illustrate how we visualize it on aggregate. Next one. In fact, this route can be coded as a library. We have many heuristics to identify different scenarios. The simple one will be, let's say, identifying a vehicle turning left or right. A more sophisticated one is that we can identify vehicle on a curvy road and the pedestrian on the road. So we have a growing set of library to identify interesting scenarios. Next one. All right, so Steffon mentioned there's a higher level concept at ATG. One of the higher level concept is called an event. So naturally, event has a start time and an end time. And we can attach any arbitrary metadata to this event. For example, the UPS truck in front of us, we can attach the speed and acceleration, which are 0 in this case. And just to illustrate that we have a very elastic data structure built in ATG. Next one. And we have a visualization tool to sort of sample those mined events at scale. If you're loading a bunch of events, you can just manually sort of check the false positive with this tool we built, which is, I find is pretty convenient. Next one. And another benefit of have those pre-mined events is that you can really throw it on the map and just observe the interactions of different actors. This is great. This is very beneficial because it helps autonomy engineers to build intuitions on the scenario and to reason about what capability they need to build for the specific scenarios. Next one. And here's another magic power if we are working with events. So we can use simple event to compose more sophisticated events. For example, if I want to identify a pedestrian crossing the road while a vehicle is turning left, I can see the intersections between those two events. And we have a timeline to visualize and to analyze those in different interactions of those simpler events. Next. All right. Next slides. So like Steffon mentioned, we're able to take a look at scenario space at the aggregate level. The scale provides us a unique perspective on what's common and what's unique. This provides tremendous business advantage. Next slide. For example, this can help model trainer to identify real edge cases. Let's say we have a new event. The blue line in the graph seems to be very common, very vanilla. Next slide. By contrast, the magenta line is really unique. The model trainer then can collect a set of unique scenarios and improve their models using this data. From a cost-saving perspective, we can be biased toward unique events. For example, having a longer time to leave TTL for those logs. For example, next one. And this is another representation of the scenario space shown before. Next one. Well, in fact, when we have question of how much driving is enough to develop a specific autonomy capabilities, we can reason this very precisely using statistics. For every scenario attributes you saw in the previous slides, we can infer the statistical significance, i.e. confidence interval and margin of error, etc. People or decision maker can calculate the ROI of the self-driving operation by looking at the margin of error. This can reduce the cost and increase diversity of your training data. Next one. So those statistical analysis can be applied literally to any attributes you mined with this data mining operations. With that, let's go into the Q&A section.
Well, thank you very much. Thank you for the presentation to both of you. Of course, let's start right in. The first question we got was rather specific about slide 24. I'm not sure if you can go back that quickly.
Yeah, I'll pull it up. Yeah, I'll pull it up.
The question was about what happened with the pedestrian crossing observation at about observation 250, because there was a spike in the average, a big step in average. That's the question.
Yeah, great question. So let's see what we can learn by looking at this this series itself. So I think you're referring to this spike right here. Mm-hmm. So looking at the raw plot, we can see that we started getting some of those joggers for the very first time. So the first, 200, 220 so observations, it's mostly people walking the street. And then we got some joggers. So those first values, especially early in the collection cycle, it looks like it impacted the average. And you're right, we can see that spike right there in the early observations.
Mm-hmm. So in general, are there a big difference, or can you maybe also elaborate on the model, whether one person is crossing the street, or if you have, like, I'm thinking about very busy streets, maybe also in San Francisco or something, when there's like a whole bunch of group of people, and some in the forefront are walking slow, and in the background somebody's running. How difficult is it to actually catch all of that?
Yeah, absolutely. So the example analysis that we looked at was dealing with the atomic level of looking at each crossing individually. And then, as Shouheng started to allude to, is you can layer all these individual events on top of each other, allowing you to construct queries that would say things like, okay, show me all of the moments when there was 2 simultaneous crossings, or 10 simultaneously crossings, or 10 simultaneous crossings with a vehicle also turning into the intersection, or 10 crossings on a straight road versus 10 crossings on a curvy road at night, right? You start to be able to join across all of these data mined outputs.
Thank you. Another question we got was regarding the events. Does UTG define its own event library, or is there an industrial standard for it?
Yeah, that's a great question. From my point of view, it seems like the industry is trying to evolve to the point of having a set of standards. Yeah, I'd like to think that this work is positioned to contribute to that, but in my mind, that seems to be an open question. Okay.
So like just a quick follow-up, what would you say is that mostly dependent on, or where do you see the development going within, like, maybe the next couple of years?
Shouheng, do you want to field that one?
You mean the standard library of events?
Mm-hmm.
Well, if you think about the interactions between actors, right, there might be, well, there's infinite type of interaction, but my suspicion is that there's only finite valuable interactions between the different actors. For example, if people are on the collision course with each other, right, if we can capture, let's say, 80% of the interaction by providing a standard library, we can mine very efficiently in the future. Whenever, whatever your source is coming from, it could be the log from the Uber ATG, it could be Waymo. So I'm definitely optimistic about coming up with a standard set of library. Just try to imagine how many crossing pattern is there on the in intersections, right? I believe if we can develop some common heuristics or models, it will probably cover most of the cases. Then it's just a matter of identifying corner cases if we want to improve the library. So I guess that's my answer to. This is my
I think that's a perfect answer.